right, there we go. All right, so we were going to review basically the tutorials that we've been running through today in a more on Monday and Wednesday on error handling, and introduce these concepts that we've been covering more formally. So again, the whole point of error handling is that some errors are predictable, some errors are unexpected, but you can anticipate them, right? You may be able to anticipate them. You may be able to anticipate errors and protect your program against them, right? This is called collectively error handling. When you write code to test for errors, right? Say divide by 0. So for example, you could say A divided by B. That's a piece of potentially dangerous code because B could be 0. So what we do instead is we check, is B 0? And then we don't divide by 0 if we're going to about to do that. You write code to test for errors and then deal with them. And then the term here is handle those errors. Handle them, excuse me, there we go. Sometimes errors can be or should be fatal. So for example, every time that you've hit exit or you've had the command exit of 1 or exit of 0 or something like that, you are choosing to make that error into a fatal error. And that's perfectly fine for some of the programs that you've been doing up to this point, because if a user, if you expect 3 command line inputs and the user only gives you 2, right? There's not enough data there for your program to execute. That should be a fatal error. But generally, it doesn't have to be a fatal error, right? You can communicate that back to the calling function to say that, look, something went wrong, you gave me bad input, you deal with it, because I don't know how to deal with it, right? And so we call that defensive programming. In C, our general strategy is defensive programming, right? Inside of a function, we test for invalid or input or error conditions, right? Then, basically what we're doing is we look before we leap, right? If we're about to do something dangerous like divide by 0, we don't do it. Instead, we return immediately from the function with an error code, right? So if you are about to do something potentially dangerous, you check for any bad or erroneous error conditions, right? Generally, you return from a function with an error code. So the conventions that we were using up to this point is 0 is going to indicate no error. Right? Oops, sorry, not negative 0, but 0. Right? There is such thing as negative 0, but we won't be using it. So 0 indicates no error. Think of it like a Boolean. And the question is there an error condition, or was there an error in executing this function? And if the answer is no, right, that means false, 0. There was no error. If the answer is yes, 1 or 2 or 3, right, this is some kind of error, right? The value of the error code tells you what type of error occurred. And the example that we went through was, what was it? I forget now. In the financial utils was what? Financial utils.c. Looks like, yeah, the monthly payment and the calculate bill, right? Negative values were not acceptable. Null pointers were not acceptable. Annual percentage rates out of the range of 0 to 1, those are unacceptable, etc. So we're checking for those and then returning a different error code indicating what happened, right? What you don't do, bad error handling, right? You don't exit, right, in a function other than main, right? Up to this point, we have been exiting if there are a bad number of command line arguments. if there are invalid command line arguments. But that's because those are simple programs. Those simple programs only have a main. Now that we have other functions, and we have functions calling functions calling functions, we need to communicate back and forth between those functions. If you have an error condition in main, there's no way that the program can even start, and it is perfectly fine to exit at that point. But inside of a function, you do not exit, right? It takes control away from the calling function, right? Function or code. Right? The example that we use is square root. If you call square root on -1, does it just kill the entire program? Is that a fatal error? No. We'll see how that is handled here in a second, but it lets you decide on what to happen, right? It's going to be the result is going to be NaN, not a number, right? And then you can decide how to deal with that not a number situation. Yeah.
Should we set up our error handling for this
Hack has this hack is 5, right? We're not expecting error handling there. You can do some error checking, but none of our test cases are going to probe that. If you write the code now to do some error checking, you're not doing the same functions in hack 6 when you do error handling, so you don't bother, right? Right. So you don't exit. The other thing that you don't do is you do not print anything. Why? Because nobody's sitting there looking at the screen saying, waiting to jump into action to see that there's an error message and, okay, now I need to deal with that, right? Instead, in practice, you use a proper system logging system. Or I should just say logging system, right? And you do want to log error messages to a system log so that you can go back and find out what happened. We won't go into system logs and see, but next semester, if you take Computer Science 1, it's definitely something I cover with respect to Java. Right? But you generally bring in a library to do it because it is far more complicated than you think. It's not just printing something out to the standard output. It is a whole bunch of stuff. You're probably printing something to a file. And now what happens when that file becomes too big? Or what happens when you want to organize all your log messages for the last day or the last hour or something like that? The library will take care of all that for you, right? And again, we're not going to get into it now, with respect to C, okay? So some other miscellaneous observations, right? You generally do not want to use mysterious, or yes, magic numbers. Right? Instead, use either preprocessor directives, right? That means define, right? Or unenumerated type, right? Enum. And we'll review the syntax for that in a moment here. So often people ask, well, which one is better? 6 of one, half a dozen of another. I tend to lean towards using enumerated types because if you're using a debugger, which we'll cover later on, how to use a debugger, but if you're using a debugger, the preprocessor has already erased all of your non-magic numbers, all of your terms, right? So for example, let's come over here to the H file here. If I had done this with preprocessor directives instead, right? Define no error to be 0. Then before it even compiles, anytime that I use no error, that's been erased and replaced with 0 already. Right? Now, if I'm using a debugger, then the magic numbers are just magic numbers. It's a 0, it's a 1, it's a 2. What were those again? I have no idea. I'm going to have to go back to my code to find out. But if you use an enumerated type, these terms do not go away. They're preserved in the debugger. Right? So that's why I lean somewhat towards using enumerated types. Okay? Let's review the syntax for enumerated types and the fact that you can use them for other things. Right? So many pieces of data have a fixed number of limited possible values. Right? For example, days of the week. They're not making any more. Sunday through Saturday, right? Months of the year. It's been maybe it's been quite a while, maybe 2,000 years since we've had a new month. Right? There used to be only 10 months, did you know? right? The two in the middle were because of Julius Caesar, July, and August, Augustus Caesar, right? They added their own months there. I don't know if they did it or somebody else did it in their honor or whatever. But now we have 12 months. Ideally, we should actually have 13 months. Why? We have 13 lunar cycles, right? So maybe we will add another month in the future. But months, no, nobody's adding any time soon, right? Other things would be error codes, right? Or class types, right? Freshman, sophomore, junior, senior, right? In C, you can define an enumerated type with human readable terms as your possible values, right? So let's go ahead and do days of week here. Let me go into code mode here. I won't do it over in the editor here. We'll just do it right here. Now remember the keyword that we used? It was type def. You know, I never checked the audio. Yeah, we're good. All right. We'll take those off now. So type def. Oops, I need to spell it. Def. There we go. Type def and then a enum. Right. Now, you might be asking yourself, are there other types? And yes, we will get to them. There's a structure that we'll definitely cover at the end of, towards the end of the semester. It's a way to collect pieces of data into one logical unit called encapsulation. So type def enum, and then you start giving it a list. Well, for most people, the day of the week starts on a Sunday, right? Then Monday, right? Then Tuesday, Wednesday, right? And just as months of the year, two of them are named after Roman emperors, each one of the days of the week is named after something. Sunday, Sun's Day, Moon's Day, Tyre's Day, Wednesday is Odin's Day from Norse mythology, and then everybody knows what Thursday is, right? Thor's Day, right? The god of lightning or whatever, thunder, whatever it is. Friday, or Freya's Day, and Saturday, right? Saturn, right? Roman god. Yeah, that was a Roman name, right? Okay, whatever it is, right? How did I go about listing this? It's a list, comma delimited. Now, generally, white space does not matter, so you could have put them all on one single line like this, but that's not as readable, is it? Right? So I tend to put one thing per line all the way down. This last comma right here is the coding Oxford comma, and it is optional. You don't need to put it there, but a lot of programmers do. Okay? Then you finally need to give your type a name. Just as an integer, its name is lowercase int. A floating point number, its name, the type of the name of its type is double. We'll have day of week. Day of week. There we go. And then a semicolon at the end, because it is a declaration. Just like a function prototype, just like a variable declaration, you have to have a semicolon at the end. Right? Now, some observations. Right? On style especially, we use upper underscore casing for list items. Now, each one of those was just a single word. But if you want multiple words, like error codes here, then you separate them with an underscore. You don't ram them all together because that is difficult to read. Right? Negative input error, if that was rammed all together, then it'd be hard to parse that out. Where does that word end and the next word begin, etc. So we use upper underscore casing. Now, why do we go all uppercase? Because these are essentially constants, right? Sunday is not going to change. Monday is not going to change. Right? Those are constants. Those are fixed values in our enumeration for the actual list items. We use upper camel casing. Now remember, it's called camel casing because a camel's hump goes up and down. So the first letter in each word is uppercased. All of them are, all the rest are lowercased, and of course no spaces because you can't have spaces for the names of the enumerated type. Now, that is right here, day of week. Capitalized day, capitalized O, capitalized W, right? You can use other conventions as long as you're, consistent about it. But this is the one that we're going to suggest, right? One item per line, separated by commas, right, etc. Now, later on in your program, you can use your type. So let's take a look at an example of the usage of this. If I want a day of week, then I can just create one today. Right? That's just like creating an integer. Right? If I want an integer, I would say int x, right? And that creates an integer variable for me. If you want a day of the week variable, now that you've defined this later on in your program, you can use that as a type. And that's why we use upper camel casing, because I use lower camel casing for variable names. Right? So if I had day of week, right, that's a bad variable name to begin with, but you don't want to confuse the type and the variable name together. Right? Today. You can set it equal to whatever is in your enumeration. Today is equal to Friday. There we go. Because you defined it in your enumeration, it exists now. That keyword exists. It's not a keyword, but that value exists. Right? You can even reset. You can even check for it. Right? If today is Saturday, then printf. High hopes, no hopes. Let's play the game. Even so. Even though it's probably a foregone conclusion, right? So you can check for is Saturday, right? Be careful. How does this actually work? How do enums actually work, right? Internally, enum is just syntactic sugar. For int variables. Now, what do I mean by that? Well, syntactic sugar is a term that we use to indicate that there's some feature added to the language that makes it a little bit sweeter, right? For example, in regular Old English, we have hundreds of different ways of saying that something is good. Good, great, awesome, cool, great. No, and then I repeat, right? Why do we want so many words to mean basically the same thing? It's because it makes the language richer. It makes it easier to speak, right? It gives nuance to the language. With respect to code, we also have syntactic sugar. We have additional features that are implemented with other features that make it a little bit more flexible, a little bit more easier to use. Enumerated types are exactly that. They give human-readable characters or human-readable values to an idea. But at the end of the day, they're still just integers. Right? Each value in an enum is just an integer. Right? The list begins with 0 and is incremented by 1. So for example, in the example above, Sunday has a value of 0. Monday, because it's the second in the list, has a value of 1, etc. What about Saturday? Because you start at 0, Saturday is going to have a value of 6. Now be careful. Just because they are integers doesn't mean you should treat them as integers. For example, what could I do? I could say day of week is today, and I'll set that equal to immediately to Friday. And I want to go to tomorrow. Right? So day of week tomorrow is equal to today plus 1. That'll work perfectly fine, right? Friday, what comes after Friday? Saturday. Now, what happens when I go one step further? Day of week, next day. We don't have a word for it, the day after tomorrow, right? But I'm not going to write the day after tomorrow. Right, there we go. Is equal to tomorrow plus 1. Stupid variable name for a stupid operation. The day after tomorrow. What is the day after tomorrow? Sunday, right, in real life. But what ends up happening here, right? We have Friday. Friday plus 1 is Saturday. Saturday plus 1 is, remember, Saturday is 6. So Saturday plus 1 is 7. Do you see an 8th day? Nope. It's 0, 1, 2, 3, 4, 5, 6. So 7, it's not even in our enumeration anymore. Right? And this is perfectly valid code. This will run. It just won't be equal to any actual day. It'll be day 7, right? And it's invalid, right? To drive home that point, what if I did today plus 30, right? I'll say today is equal to today plus 30. In other words, I'm going to go ahead and go to next month, right? That's not going to work, right? This is a valid operation, but nonsense results, because it's going to end up being Friday, which is 5 plus 30, 35. There's no such thing. Now, this example was with days of the week, right? If you do want to do something with respect to time, durations of time, periods of time, from one day to the next, days of the week, right? Hours of the day. Don't make it complicated. Bring in a library to do it, right? And there is a time library, time.h in C. It's terrible. We're not even going to require you to use it. But in any language, don't try to do time for yourself. Because as I said, sometimes they do add stuff, right? 2,000 years ago, they added 2 brand new months to take it up to 12. They're not adding any days soon, but you know, the one thing that is of practical consequence is, at least in the last year, they've thought about getting rid of daylight savings time, right? In fact, there was a bill that was passed in one part, in the Senate, I think, maybe not the House, but they were going to eliminate daylight savings time in the United States, right? Good idea. It just hasn't gone forth yet. What happens when if they eliminate daylight savings time, right? Now you got to go back and change all your code. No. Bring in a library to do it, and it takes care of it for you. Okay? All right. So the takeaway there is you can treat them as integers, but do not treat them like integers. You can, but you shouldn't. Okay? All right. How does C do error handling? So internally, the C language does define 3 error codes. There we go. One of them is EDOM. One of them is ERange. And one of them is darn it, I'm not going to remember it exactly. There we go. EILSEQ. EILSEQ. There we go. All right. So EDOM is going to be an error in the domain of a function. In other words, input. Now you might remember back to high school mathematics, or maybe even before that, I'm not sure, maybe middle school mathematics, that when you have a function, you have a domain, the x-axis, and then you have the range, the values that you map to, right? So x is going to be the input, y is the output on a function. The output is called a range. So this indicates an error in the range of a function, right? The output of a function. The third one is actually an illegal byte sequence. I cannot write code to intentionally cause that, right? I can write code to intentionally cause an EDOM or an ERange error. Let's take a look at what that looks like. Again, these are all the only 3 that are defined by the language itself. Let's say Emacs. What is it called? Error demo. There we go. All right. All of this stuff is handled in this error no library. Error no, it's not no error. NO is short for number. I think it's very British. I don't know why they called it that. But that's the error number library. Right? These are defined along with some tools in the errorno.h library. Right. Generally, you will not use this library directly, right? Because it's not going to be all that useful. When you do your own error handling, you're going to define your own error messages and your own error codes. But you should know about this, because this is basically where we're taking our cues from on how to do error handling. Okay. The error no actually defines this global variable called error no, which is an integer. Right. In the event of an error, this integer value is changed to one of those error numbers. For example, if there's no error, like I'm trying to do the square root of b, which is 2. The square root of 2 is 1.41 and some change, right? So it's perfectly valid. Let's go ahead and look at that output. GCC error demo, link in the math library. And let's run that. Now, ignore the rest of this for now. Look at a successful run. We computed the square root of 2, which is 1.4142. The error code, what is that? 0. What does 0 indicate? No error. Everything's fine. Right? Now let's go back into the code and see what happens here when we do have an error. For example, square root of a. A was set to be -1. Now, remember, in fact, we can pull something up. Graph, let's see, Wolfram Alpha. Graph square root of x. There we go. So take a look at that graph right there. Is it defined over here for negative values? Remember, the x-axis is your input value, right? That's the domain. So is it defined for -1? No. In mathematics, what would we call that? Square root of -1 is I, right? For an imaginary number. Over here, though, we don't have complex numbers. We don't have imaginary numbers. So the result is going to end up being not a number, and the error is going to be raised here. Once again, let's take a look at that output. I'm not going to run it again. There's not a number, and the error code is 33. Remember, these are magic numbers, right? So if you're just printing it out as a raw integer, then you're going to get just the number, 33. However, you can check for it, and that's what the code down below is doing. If the error number is an EDOM, then we'll print out that it was an error in the range, or in the domain. If it was an ERange, then we'll print out that it was an error in the range, right? There's no way that we can get an illegal byte sequence intentionally, so that's never going to happen. Otherwise, it was some other error, okay? And so consequently, we've got an EDOM error. You can also convert this to a human-readable error message. In this case, the numerical argument was out of domain. Not that useful. Right? What happens when we have an example of something that is out of the range? There we go. I'm trying to take the natural logarithm of some value. What would the natural logarithm of some value look like if it was a bad range value? Well, let's come back over here to Wolfram Alpha and let's look at the natural log. What does it look like? Right? So it's not really defined for negative values, but what happens, say, right at 0? Which is what C is doing here. C is 0. What's the natural logarithm of 0? All the way down to what? Infinity, negative infinity. So we end up printing out, indeed, it was negative infinity. And the error code here is 34. Again, just another magic number. But you can check for it, and you can also output a human-readable error message here. Again, these are not that useful. Numerical argument is out of range. Numerical argument is out of domain or out of range. It's unfortunate that they only define 3. However, there are other standards that define more error codes. Right? So, for example, the POSIX standard, which stands for Portable Operating System Exchange. Don't ask me how they got IX out of it, but let's look it up. What is POSIX? Portable Operating System Interface. There we go. So don't ask me where they got the X out of that. Interface. There we go. Right? Every operating system out there today, worth anything, is going to be POSIX compliant, meaning that there is this other standard built on top of whatever language that you're using that's going to define even more stuff. There's only one operating system, major operating system, that I know of that is not POSIX compliant, and it is Windows. Right? Don't ask me why. They wanted to do their own thing. Right? So what do those error codes look like? Much, much, much more. Right? Now, if we search really hard here, we'll find those two values that are defined by C. EDOM. There we go. There it is. Mathematics argument is out of domain of the function. Right? ERange. There we go. The result is too large, right? Because it's negative infinity. They've redefined the error messages here, right? But otherwise, you've got a whole bunch of other error messages that are compliant with this ISO, whatever this ISO happens to be, right? The argument list is too long. E-access, permission denied, connection refused, connection aborted, connection reset, right? If you're doing networking stuff. So if you're doing low-level system stuff, this stuff is absolutely necessary. There's illegal byte sequence right there, right? Input-output error, right? Too many links, too many open files, message too large, network is unreachable, et cetera, right? So you've got all these additional ones that if you're going to be doing systems programming and it's POSIX compliant, then these are all going to be available to you. Again, it's not something that we're going to use directly, but it is something that you should know about, right? And then there are various other extensions, right? But at the end of the day, in user land, right, user land, and in other words, our programs, you generally need to define your own error codes and enumerated types, etc., and do your own error handling. So best practices. The first best practice is in a function, when do you do error handling? Checking. I'm asking you, when do you do it? Here's my function. It does everything. Then it checks errors at the bottom? No. First, right, and foremost, always do error checking, handling before any actual code. Right. Okay? So suppose that you're checking for multiple different types of errors. Right? For example, which comes first? Null checks or value checks. Right? In other words, like something like greater than or equal to 0. Right? So if you've got a pass by reference variable, do you check it to see that it's positive, and then you check to see that it exists? And that doesn't sound right either. You check to see if it exists, and then you check to see if it's positive. You always check pointers first. Right? Okay? Otherwise, you are, or may, be dereferencing a null pointer. At which point you remember Bret Hart and you knock yourself upside the head. I've got a segmentation fault. Make sure not to do that. Right? Again, don't do's. Don't. Exit in a function other than main. Don't print anything. Especially on code post, if you have, you may be getting away with it. You may not be getting away with it if you're doing extra output that should not be there. Then it might count it as wrong, depending on how we set it up. Otherwise, certainly when we look at the output and we're manually grading and we see all this other weird stuff there, then we'll take off for it. Right? Return if an error occurs, return with an error code. Do not move on and do other things. Right? Again, you've already determined that you don't have enough input to continue. You've already determined that there's an error condition that you have to take care of. Don't bother doing anything else. Right? Just immediately return. Right? The general form is going to be a collection of if else statements, right, with return values. The rest of the function should not be in one giant else statement. Right? If you're returning from a function, that's the end. That's the end of the function. Right? Don't have if error, do the return, if error to return, else, and then you just put everything else into that one big giant else statement, right? Why? Because now stylistically you have increased the indentation for no reason, right? Let's go back to our example over in the financial utils, right? Over here. There we go. Right? I didn't put an else statement here. Right? I could have, but it would have been superfluous. It would have been cruft. It would have been extra code. Why? Because each one of these has a return statement, right? If one of these is correct, or if one of these evaluates to true, that's it. That's the end of the function. Right? There is no need to put the rest of the function into an else statement. Instead, you just put it outside. Okay? For no error, be sure to return 0 for no error. All right? Omission of a valid return statement may lead to garbage results. Right? So be careful. Right? What I mean by that is, let's get rid of this return statement right here. Right? And let's go ahead and try to compile it. Finance, yep, there we go. GCC C financeutils.c. Oh, it compiled. What am I returning? I have no idea. Let's find out. We have enough time. We can go ahead and, for now, I'll just go ahead and comment all that stuff out. What function was that? There we go, get monthly payment. And let's go ahead and call get monthly payment. Foo is equal to get monthly payment. What were they? Yeah, let's get rid of it. Get monthly payment should be, I'll copy this for a second here, just to remind myself of what it is. Principal, so let's go with $10,000. I don't know, 5% interest, number of years, 5 years, and then a dummy variable here. Foo is what I want, with an ampersand in front of it, and then I need to declare it. Double foo. There we go. And there, call that. But I need to capture the return value. Code is equal to that. I wonder what that code will be. Printf. I'm not returning 0, remember? Right? So maybe it becomes 0%. %d. Error code was %d. End line code. Let's find out. So I've already compiled that. Great. And by the way, if I had done this correctly and used the wall flag, guess what's going to happen now? It's going to tell me about that. Right? It's not an error. It's just a warning. But always, always, always go with the wall flag, because it's going to tell you you reach the end of a non-void function without actually returning anything here. Okay? But let's see what happens. GCC demo finance utils.o, and probably the math library there. Let's run it. Does that look like nothing bad happened to you? Is that a 0 error code? No. What is it? It's, what is it? Ooh, wow, it's huge. 1, 2, 3, 1, 2, 3. There's 1.37 billion, right? So no overflow there. But what is that number? It's whatever happened to be there before, right? It's garbage. It's dead beef, right? And I don't know, if I run it again, probably the same value. Yeah, over and over and over again. Remember, that stack frame gets destroyed, right? It's expecting the return value in that stack frame. If it gets destroyed and you are expecting a 0 there, you're just going to get garbage results. So make sure that you are always returning with a return statement somewhere, right? And of course, reminder 1,000,002, always use the wall flag. Right. It'll tell you that you've reached the end of an invalid return statement. Okay. Oh, we got done way quicker than I thought today, unless I was missing something. I don't think I am. I did everything. There they all are. Again, you're not going to reuse those directly, but you should understand that they're there. So, any questions? No? All right. Well, then continue. I'll see you on Monday.